All right, so part two, second video, chapter 4. What we're doing is we're meshing 4.1, 4.2 together into one video, or I should say multiple videos. And this is the second part. So recall that the topics are vector spaces and subspaces. All right, and last video, I gave you some definitions, then tried to give you an analogy of a way to think about a vector space and a subspace using Netflix. And then we practiced, or what we said is we're going to start with subspaces, and then we're going to work our way to vector spaces. Okay, so let's recall if it's been a second. What are the three axioms that must be met in order to say that a particular subspace is indeed a subspace of some vector space, right? So these were the axioms. So subspace for some vector space V has to be closed under vector addition, closed under multiplication by scalars, and it has to have the zero vector, okay? All right, so let me read the question, and listen, don't get stressed if this is hard, because you will get pretty good at this, but you'll have to trust me, and you'll have to just bear with me, okay? So what we're going to assume is that R2 is the vector space, right? In other words, every single point that you could, xy point that you could plot in R2 space is how we define our vector space. Now, notice that what we have here in this picture is just a highlighted subset of all of R2, right? We just have a smaller set, a piece of R2 space, of R2, the R2 plane. And now what we're going to do is let me read the question, and we are going to try to figure out if this is a subspace of R2. All right, ready? So it says, let H be the points inside and on the unit circle. Now that is just a description, a verbal description of what I've written here in yellow. So the way that we read this is we say H is equal to the set of vectors such that x squared plus y squared is less than or equal to 1. All right? Now, our job is going to be to find, right, to find two vectors, u and v, or a vector and a scalar, right? You have a choice. So find two vectors, u and v, ready, that prove H is not a subspace of R2. So in the game that we're about to play now is we're actually going to see if we can pick either a vector, two vectors, or a vector and a scalar, and prove that one of these axioms don't hold. And if we can prove that one of these axioms don't hold for a single point, then in that set, then we get to say that the entire set is not a subspace of R2. Okay? So just one single instance will discredit this this proposition. So ready? Let's go ahead. Let me give myself a little bit of space. And how are we going to do this? Well, let's see here. First, let me, as we're starting to go along, the first thing I would do, if I'm you, if I'm a student, I'm in your seat, the first thing I would do is start with the zero vector, right? Because if the zero vector is not in this highlighted region, then automatically we can say that it's not a subspace. right? But if you take a look, the origin, the 0 vector 0, 0 is in this highlighted region. It does meet the requirements that were mentioned. So all right, so far we don't have anything to show that it's not a subspace. So let's go to the next part. So I'm going to pick some vector u. Ready? So I'm kind of looking, remember this is on a unit circle, so that means so we have a radius of 1 on this circle. So the game becomes, can I choose some value that's relatively easy to work with? Okay? How about 0.5 for x, 0.5 for y? So if I kind of try my best to plot that, so that would be the midpoint between 0 and 1, and this here would be the midpoint between 0 and 1, and I'll do my best to try to capture that particular point, u. Okay, so that is u. That vector u is when x is equal to 0.5 and when y is equal to 0.5. Okay, so now let me see if I can pick a scalar, right? And the game is we are allowed to choose any scalar we want, but we are trying to prove that this is not a subspace. So let's pick, I don't know, let's pick 4. So we have c is equal to 4, and we have u, vector u is equal to 0.5, 0.5. All right, now follow me down here to the axioms, part C, that says H is closed under multiplication by scalars if for every u that is in H and each scalar c, the vector cu is also in H. Okay? So let's you and I agree that for sure, u is in H. And what we're going to do is we're going to say, we're going to let c, the scalar c, multiply by u. Now, in this case, we chose a scalar of 4. We chose a vector of 0.5, 0.5. If we distribute that scalar, we get a new vector. The new vector is cu, and half of 4 is 2, 2. All right. Is 2, 2 inside or on the unit circle? Well, no, right? I mean, 2, 2 is not even, I can't even graph it. It's outside this, for sure it's outside this circle. So what did you just do? You just proved that u is a vector in the shaded region, but cu is not a vector in the shaded region. And that means that this axiom fails. U is in H, and we picked a C value, but Cu was not in H. So that's one way of showing that this subspace, or this subset of R2 is not a subspace. Okay? Let's go to another example. All right, ready? Let me read. So it says, show that the set H is not a subspace of R3. Okay, so now we are in R3 space, in three-dimensional space, and we want to show that this set H is not a subspace of R3. Ready? So in this case, just kind of working on our vocabulary a little bit. What is what is R3? Well, R3 is all the points that are in space. Okay, that's our vector space. So our vector space consists of every single three-dimensional point, every x, y, z point. All right, now take a look at the graph that I've produced here. This red region is the subspace that we are dealing with, right? So we agree that that's not every single point in three-dimensional space. That's a subset of R3. All right, ready? Let's go ahead and read this notation. I'm gonna take a second and highlight. This is not me being sloppy. Well, it is kind of me being sloppy, but I'm trying to make that R a certain way, and I'll explain it in just a second. Ready? So let's read. We're gonna let H equal, here we go, the set of all x, y, z points such that the x, the y, the z is in R. Now, what do we mean in R? We mean that means the x, the y, the z are real numbers. They are real numbers in you can think of it as one-dimensional space, right? They're on the number line. All right, one more time now. So H is the set of all points in space such that the x, the y, the z is in R, meaning they are real numbers, and x squared has to equal z squared. All right, so let's go ahead and bring in our conditions that must be met in order to say that it is a subspace. Okay, so as I said, the way my suggestion to you is the very first thing you should do is check to see if the zero vector is in the subset, right? And as of right now, you can see from the graph that our region crosses the origin. But even if that's not the case, right? So even if that weren't the case, we still could show that if x is 0, y is 0, right? Let me write this a little bit better. So what am I doing right now? I'm trying to show you, well, let's assume really quickly you don't have access to some three-dimensional grapher, right? Some three-dimensional plotter, and you're thinking to yourself, man, how am I going to do this? How am I going to show that the zero vector, or know that the zero vector is actually in the subspace? So, well, that's okay. You can do this. Let's think of it like x is defined to be 0, y is defined to be 0, and z is defined to be 0. That would be the zero vector in R3. Right, that would be the point 0, 0, 0. Okay, now let's go up to our criteria. Is 0 a real number? It is. So the first condition is met. All right, now let's go to the second condition, which is x squared must equal z squared. Well, since x squared must equal z squared, if I chose 0 for x and 0 for z, 0 squared does equal 0 squared. So do you see how you can show that the zero vector is an H, regardless if you have access to some type of three-dimensional plotter? All right, so now let's continue. Let's see what else we have to prove. All right, so what I'm going to do is I'm going to go to I'm going to go to vector addition. Okay? So in order to say H is closed under a vector addition, that means, well, the game is we have to choose a vector U, and we have to choose a vector V. Okay? Now, the game is U, where you can, it's up to you what you want to choose. But U has to be in this shaded region. It has to be in H. And V also has to be in H. So let's start. I'm going to choose, I'm going to do it this way just so we can work with some numbers just a little bit more before we start working with simply x, y, z. So I'm going to choose the vector 1, 1, 1. That's going to be for U. Now let's agree that let's you and I agree that 1 is in this shaded region, right? And let's do it this way. And the 1 for x, 1 for y, 1 for z, these are real numbers in R1. And if you set 1 squared equal to 1 squared, that is still a true statement. So U is definitely, right, vector U is definitely in H. Let's now pick another vector, V. I'm going to choose 1, 1, negative 1. Okay, so 1, 1, negative 1. Are these real numbers? They are. Okay, what about if we plug them into x squared equals z squared? Well, x would be 1, so 1 squared is 1. Z would be negative 1, and negative 1 squared is also 1. So do you see how U and V are definitely somewhere in this shaded region? Now that's great, except that's not how you show that it's closed under addition. To show that it's closed under addition, we have to take a look at what U plus V looks like. Because U plus V must also be in this shaded region. Ready? So let's go ahead and do our math. So we have 1, 1, 1 plus 1, 1, negative 1. Ready? Let's produce a result. So 1 plus 1 is 2, 1 plus 1 is 2, and 1 minus 1 is 0. So what is this vector that I just wrote, 2, 2, 0? That is the vector U plus V. Now let's go back up here and figure out if this new vector meets our requirement. So let's start with the easy one. X, Y, Z, they have to be real numbers. 2, 2, 0, these are real numbers in R1, so that's good. But now x squared has to equal z squared. So do you spot it already? That if you have x equal to 2 and you have z equal to 0, 2 squared is 4, 0 squared is 0. You end up with a statement that, so 2 squared must equal 0 squared, and this fails. This fails to meet the condition. What does that mean geometrically? Okay, what does that mean? That means although 220 is a point in R3, it's not in this shaded region. It's not in H. So what did we just figure out? We just figured out that this fails the axiom of being closed under addition. And so as I mentioned, you have your work cut out for you if you're just going to pick points until you find one that fails. Because what if none fail. Are you just going to pick points all day long, right? Are you going to pick points forever? So do you understand that not a game that you're going to win if you if your only route is to just choose numbers until you'll see if it fails? Because what if it doesn't fail? What if it actually is a subspace? Well, then you're wasting a lot of time. So, but in this case, what we're doing is sometimes it's fairly easy to spot, right? Sometimes it's pretty easy to spot that, hey, this is not going to work by choosing a few values, choosing a few vectors or a vector and a scalar. So let's continue. Now, in this case, let's see what the question's asking of us. So we are asked to actually, in this case, we're asked to show if now I use W. If you don't mind, I'm going to change that to H just so it meets the three axioms, or it's using the same notation that three axioms are using. So let me read this. So it says, let H be equal to the set of all vectors x, y. Now, what space are we in? Well, if you're in x, y, that's if your vector is a 2 by 1, then you're in R2 space. Okay, so H is the set of all vectors, and here's your condition. But the x has to always be 0. Right? Let's actually write what that would look like. So that would mean that every vector that's in H would have a 0 for x. But there's no constraints on y. So you can choose any y value you want, but the x value has to always be 0. Now what I'm going to do right now is I'm going to go ahead and draw what that subspace or potential subspace would look like, right? So if x is always 0, but y can be any value you want, then you just have a vertical line, right? Just have a vertical line, x equals 0 in your graph. Okay. So ready? Again, working with a vocabulary. What is the vector space? Well, the vector space is all of R2, right? So every single xy point in R2. Now, what is the potential subspace? The one that's under scrutiny right now is H. Ready? Now the game begins. Can we show that H is a subspace of R2? Okay, so let's start, as I've mentioned numerous times by now, let's start with the easiest place to start, which is the 0 vector in H. So is the origin on this blue curve? It is, right? So we are, the first condition is met. Okay, and now where do we go from here? So at this stage, I'm going to make this a little bit smaller so I have some space to work. But we're going to go to addition, closure under addition. Okay, so let's not do it, let's actually make this a little bit more formal this time, instead of just trying to pick random points in H. So let's think about the possible scenarios for vectors, right? So we're going to pick some vector u, and we're going to pick some vector v. Okay, so what are some options what are some options of points that are on this blue line on this in this set H? Well, we have no options with x because x has to be 0, right? However, what are the options for y? Well, you could have a positive y. You could have a negative y. You could also have a 0 for y, but we've already shown that that meets our requirement that the 0 vector is an h. So now let's think about some possible scenarios that could come out of this, right? So what would happen if I chose, so we're going to look at u plus v, we'll look at a couple different scenarios here. But by the way, the way I'm teaching this is not the way I would do this, but I think it's, in my opinion, it's the best way to train you. Okay. So, as of right now, I'm going to try some different things, actually. And so I'm going to try this. I'm going to try to say, well, what if we chose, since these are the options, y can be negative or positive, let's say we chose two positive y values, right? So y sub 1 is a positive number, y sub 2 is a positive number. And now let's see what that would look like if you had u plus v. Ready? So 0 plus 0, we still have 0. And then for the y value, you would have a positive y value plus another positive y value. The way that you normally would do this is you would, let me give you the intuitive way of thinking about it, and then let me come back and show you like a more formal way of thinking about this. So intuitively, if you have a positive y number plus another positive y number, you still have a positive y value, right? So what we would know is that u plus v, if you pick two positive y values, you would have the 0 for x, and you would have some positive y value for y. And that is, you could still graph that, right? That is still on that blue region. Now, a much better way of thinking about this is to redefine y sub 1 plus y sub 2 as being y. And if that's the case, then we would have the vector 0, y, which is exactly what we said h should be. Okay, are you starting to get the game that you're playing? Is it starting to click a little bit better than on the first few videos? So what if you were to choose two negative y values? So now let's let y sub 1 be a negative number. Let's y sub 2 be a negative number. Let's hurry through this. If you add u and v, you would get 0. And then what you would have here, it would be if you have a negative y value plus another negative y value, negative y sub 1 minus y sub 2. Do you understand that you still get some vector 0, but now you have a negative y value? But it's okay to have a negative y value. It's okay to have any y value you want, right? The graph of x equals 0 simply says that x must be 0, but y can be it can take on any value. So what are all of this to show? That you have both, yes, you have closure under addition, and we have the 0 vector. So we are working our way towards being able to make the statement that this is a subspace of R2. One more axiom that we have to show. Okay, so let me go ahead and clean this board up a little bit. and then I'm going to give you kind of a tip of the way I would, of what order I would approach this in. Okay, so the very last axiom is to show closure under scalar multiplication, right? So we're going to we got to pick a vector u, and we got to pick a scalar c. All right, now, what are our choices? So our choices for vector u simply says that the x has to be 0, but we can choose a y value that's positive or a y value that's negative. Of course we can choose 0, but that's a duh statement at this point. Right? So or these are our choices for vector u. What are our choices for vector c? I'm sorry, for scalar c. Well, you can choose a negative c value or a positive c value. So you can have a negative c or a positive c. And the game is there any multiple of c times u or negative c times u such that cu is not in this blue region? Okay, so let's assume that we were to choose a positive c value. And we'll put a 0 here and a y here. And then at the same time, let's go ahead and say, well, what if we were to have chosen a negative c value? Let's see if we get anything that would rule out this axiom. Well, a positive number, a positive scalar times 0 is still 0. And a positive scalar times y is still another y value, right? What about a negative scalar multiplied to 0 would still be 0, and a negative scalar multiplied by y, what would that be? That would just be another y value, only now it would be a negative y value. Can you see how this is not a problematic statement? We have access to all the y values, including the positives, the negatives, and 0. Neither one of these are problematic. In other words, h is also closed under multiplication of the scalars. We have met all three axioms. So in this case, h is a subspace. Subspace of R2. All right. So we don't get any better at math unless we keep doing math. Okay, that is the scenario. So we have to keep playing this game. So in this case, we're going to let h be defined as follows, right? Does that maybe let me, I'm going to erase what I'm about to write, but maybe I can help you. If you think in terms of x, y, z's, if that helps you, then of course h is in three-dimensional space, right? We have an x, y, z. Only in this case, we can think about the z value is always going to be x plus y. Does that help you a little bit better to understand what this space looks like? Okay. Now, what is the vector space? What is V? Well, vector space is all of R3. That's all the points in space. And what is the potential subspace? That is H. That's the region where you have x, y, and your z values. Your height is always going to be x plus y. Okay. So let's start with our axioms and see if we can show that this is a subspace of R3. Again, so now let me give you some tips. The way that I normally work these, if you gave me these problems, the order that I would do them is I would start with the 0 vector because that's the easiest. That's the easiest to spot. And then start here, and then I actually would probably go to scalar multiplication. This is just a preference. I tend to find that easier. And then last I do closure under addition. Now I'm going to just do it in the order that it's stated, but that is the way that I would do it if you gave me this problem to do. So let's start with the 0 vector. Is the 0 vector in H? Right, so what would the 0 vector look like? So that would be 0, 0, 0, x is 0, y is 0, z is 0. So the question is, does that meet our requirements? So that would mean if a is 0, right, if a is 0 and b is 0, is a plus b also 0? Yes. So we do have the 0 vector in this space. Let's see if we can show closure under addition. All right, now what would be the game? The game would be to pick two vectors, u and v. And the game would be to show that u plus v is also in H. So notice what I've done here is I've just chosen, I've labeled for vector u, I've labeled a sub 1, b sub 1. So that would mean that the z value would be a sub 1 plus b sub 1. And I did the same thing for vector v, a sub 2, b sub 2. And that would mean the z value is a sub 2 plus b sub 2. So let's see what u would look like, or u plus v would look like. So this would be a sub 1, b sub 1, a sub 1 plus b sub 1, plus vector v, which would be a sub 2, b sub 2, a sub 2 plus b sub 2. All right, ready? Let's see what that would look like. So clearly this would be a sub 1 plus a sub 2. And the y values would be b sub 1 plus b sub 2. And finally, I'm going to write this as, my apologies for running out of space here. We're going to write this as a sub 1 plus b sub 1 plus a sub 2 plus b sub 2. And I'm going to go ahead and move this. I'm going to grab this guy and give us some more space because this next step is very important. And I want to make sure you can see it better. So forgive me. Let me rewrite this. Okay, so a sub 1 plus b sub 1 plus a sub 2 plus b sub 2. Okay, so at this stage, until you've taken enough math, until you've started to train in some of these techniques, you may find yourself staring at what I've written here thinking, what the heck? How does this show me that it's closed under addition? But watch this, right? If of all the times for me to ask you to watch this and pay attention, please, right here. What if you define, right? If you define A to be a sub 1 plus a sub 2. And what if you define b to be a sub 2 plus b sub 2? But you know what's funny is that, so a sub 1 plus b sub 1 is how we're going to define a. No, I'm so sorry. I'm going to try that again. After I said of all the times for me to ask you to watch, you then watched, and then I, in my excitement, I messed up what I was trying to say. So let me try that again. What if you defined a to be the following: a sub 1 plus a sub 2. And then you defined b. Henceforward, b is defined to be b sub 1 plus b sub 2. Now watch what happens if you make these, if you define a and b to be this way. So if henceforward, if everywhere I see an a sub 1 plus an a sub 2, I can rewrite that as a. So what should I put here in that first row? Well, simply a, right? And what should I put in that second row? B. And what should I put in that third row? Well, you can always drop the parentheses, rearrange, so you can put the a's beside each other and the b's beside each other, so that I would have a sub 1 plus a sub 2, and then I would have b sub 1 plus b sub 2. In other words, what would I have? I would have a plus b. Do you take a look back up here? Follow me, follow this arrow. Ready? See, follow. That is exactly the way H is defined. So, yes, we do have closure under addition. All right. So, I'm gonna go ahead and finish this guy up. All right, I'm gonna erase everything that I have here and finish this guy up with the multiplication by scalar closure. And then I think what we'll do is what you really should do is pause the video and see if you can do it. Right? That's how you know if you're getting good at this stuff, is if you are anticipating what I'm about to do next, or and you can do it on your own. So let's go ahead and do that last axiom. We have verified axiom 1, we have verified axiom 2, and now it's time to see if we can verify axiom 3. So remember, axiom 3 says the only things that you have access to is some vector u, and then, but you have access to scalars. It could be scalar c or negative c. All right, so now for whatever vector u, we're very restricted in the sense that it has to meet, in order for u to be an h, it has to take on a, b, a plus b, right? That is the only option that we have. But what we can do is we can think about a positive scalar multiplied to vector u, or a negative scalar multiplied to vector u. Okay, and we just want to see if either one of these are going to be problematic. Let's start with a positive scalar. So this would be c scaled to the following vector. All right, so c times a is ca, c times b is cb, and c times a is ca plus cb. I'm going to, again, what looks like I'm going to have enough space oftentimes turns out to not be the case. So let's try that again. So after I distribute that scalar, let me rewrite that a little bit clearer. So C times A, C times B, and then we have C times A plus C times B. Okay. So that is the scaled version of vector U. And now the question is, well, can I get back to vector, or can I show that whatever is inside here must also be in H? Well, you can, and so I'm gonna go ahead and do this for you, and then I'm gonna show you. Again, I think the way I'm showing it right now, it's gonna make the most sense. But then I'll give just this one little tip or extra piece of information after I'm done. Ready? So at this stage, what if we were to define? What if we were to define, let's say, A sub 1 is equal to C times A. And we were to define B sub 1 to be equal to what? To be equal to C times B. So if I'm going to make some substitutions. So anywhere I see the vector CA, I'm just going to write A with a subscript 1. And anywhere I see CB, I'm going to substitute a B sub 1. So that last part is going to be CA plus CB. That's going to be A sub 1 plus B sub 1. Do you notice that what you have here is the exact form that you would expect your vector H to take on? Now the only thing that should be different is normally the way you do this is you would define U to have the subscript like this. And then you're back substituting for A instead of for A sub 1. But I think that this is clear enough, given that I can't read your faces and I can't interact with you. So I hope that this was clear enough for you to see that, look, A subscript 1, this is just some value of A, and it can take on any value. H can take any value of A. And in that case, we have met the third requirement to be able to say that it's closed under multiplication by scalars. So what is it? It is a subspace of R3. All right. So I am going to go ahead and take a break. When we come back, we're going to stay here in 4.1 and 4.2 for a little while, so please don't gloss over this information. If you have to go back and rewatch the videos, or maybe if this is I don't teach online, so maybe you have to find some additional references for it to help click. Either way, keep at it, because we need to really understand subspaces and vector spaces to proceed. See you soon.